Okay. Fabric extensions. So this is a discussion about could you have your leaf switches in multiple physical sites? And if you have any questions, feel free to use the audio to interrupt me while this discussion is going on. I cannot see the chat. That's the only issue I face right now. It's about, can you place your switches in different physical sites, maybe a DR site or a redundant site? And if yes, how should we design for it? So one of the foremost methods was, of course, something called a stretched fabric. In later releases, they added something called multiple pods. Actually, before multiple pods, they added a feature called golf. Then they added a feature called multi-pod, and then they added the feature called multi-site. So you might be able to relate and implement or identify which one has been deployed and which one you all might even expand to. Well, the deployment size is dictated by several factors: the size of your organization, how many switches do you need, how many sites do you need, so, and also the type of redundancy you require. So these would dictate the, or in other words, your business needs, cost. These would all dictate your deployment options. Okay. So since this is currently become a product for the SDN, remember there are several vendors playing in this field. We already have Arista, VMware, we have Juniper, Cisco, and Cisco has in the last 2 years seen more sales in this area. I would say purely because all customers have been kind of reaching their timeline for upgrades of their Nexus. Okay, so the customers may have deployed Nexus in probably 2009 or 10 or 11 or 12, and every 5 or 6 years they tend to go ahead and deploy newer hardware. So a lot of customers sitting on the fence trying to determine which SDN solution should they pick, because SDN seems to be the route to take. Okay, some form of software-defined networking seems ideal. So a lot of customers in the last 2 years have been trying to arrive at some vendor product, and Cisco has seen some improved sales for their data center SDN solution, which is of course ACI. And they realized that one size does not fit all, or one deployment does not fit all network needs. The type of business would dictate your deployment type or the model. Okay, the size of business, the type of business, that's why it says it doesn't fit all. Not a deployment option does not fit all organization types. So they've been evolving over the years. Okay. Well, design options could be, okay, we want one fabric, which means we have a set of APICs in the cluster. It's technically one administrative domain. And then you could spread it out in different physical sites. That's one approach. Or like some of the larger organizations I have worked with have implemented multiple fabrics, multiple clusters installed, each their own administrative unit. And of course, in 3.2, they said, well, you can actually now manage these multiple clusters through a single pane of glass and even extend your application across the multiple clusters. So that's the second option that they show you there. Golf is actually a method that they introduced in version 2.0, improves the way you connect your ACI network or your data center to external layer 3 networks. That means in our layer 3 discussion, I didn't go into any further details than connecting your layer 3 to leaf switches, and those leaf switches were called the border leaves. That's how Cisco, or they only supported that option until version 2. In version 2, they came out with another approach where you can connect your layer 3 to spine switches. It becomes more efficient and scalable, especially in a provider environment where you have multiple tenants, thus multiple VRFs. So it becomes a lot more scalable. Golf means you just connect the physical connectivity to a spine, define it once, and then you share it with other tenants. Makes it a lot easier. And that would be the golf deployment. So here it talks about the two, which are the single cluster deployment. That means we actually have the stretched fabric, or what we call the multiple pods. These are all for one cluster. Okay, a stretched fabric was supported, I would say, in 1. I can't remember. It's not the first release, but right after that. Okay, it's a 1. Some release, and essentially, initially, they said you could just deploy the fabric across 2 sites, period. So initial release of stretch fabric was 2 sites. Then they said you can go up to 3 sites. But stretch fabric would depend on you having either dark fiber or maybe even a DWDM connectivity. You could also achieve it over implementing Ethernet over MPLS pseudo wire. But then you have to ensure a 10 millisecond round trip timer between the 2 sites. Okay, so this shows you an example of a stretched fabric on the left-hand side. And on the right-hand side, it's actually showing you the same fabric. You can see it's the same fabric. In other words, it's the same cluster. Even on the left, it's the same cluster. The 2 APICs on one side, 1 on the other. And then even on the right-hand side, it's a similar one, but they have defined it as multiple pod. Multiple pod actually means you're going to have, so in this particular, oops, I'm clicking the wrong, give me a, need to move this up somewhere. So oh, where is my, so in this particular one, in the first one, we have the same session of ISIS, the same MPBGP. It's also stretched across the 2 sides. That means if ISIS fails, it affects both sides, or MPBGP acts up, it affects both sides. Okay. In this multi-port implementation, a separate instance. Huh? Why do I have that coming up there? So a separate instance of I would say ISIS first, because that's the protocol that builds the routing table between the VTEPs, COOP, and MPBGP. In each pod, and I'm putting the word pod in double quotes because there is actually a creation of a pod when you go with this design. So if I have a problem with ISIS in pod A, pod B will still work fine, pod C will still work fine. So here it's the same instance of all of my control plane protocols. So how does it transport? So if I have COOP here learning all the endpoint information in the spine, how does it share it with the spines here? So these endpoints can route their traffic across, and that's where the MPBGP EVPN, Ethernet over VPN, comes in. Okay, so that's how the multi-pod approaches. And we'll take a look at that approach. So the multiple cluster. Okay. Multiple cluster, you can have what is called the dual fabric, exactly two fabrics. And then you pretty much have some form of dark fiber between the two fabrics, okay, to send information. That's just two fabrics, that's all. It doesn't support more. But with multi-site, you can have multiple APIC clusters, and they are going to be managed by a product called the Multi-Site Policy Manager, ensuring a single pane of glass. Not only that, it also, sorry about that line coming there, not only a single pane of glass, it allows us to stretch application EPGs. Oops, what's that? Or bridge domains, VRFs, tenants, across the two or more fabrics. That's the beauty of multi-site. It is independent fabric. That means if this entire cluster fails, never affects another one. In fact, you could even use it in a certain design. You can even do vMotion across these. Okay, but this would be the most costliest, because you're going to be spending on two different fabrics, two sets of APIC clusters, their own corresponding leaf and spine switches. And then, of course, you need the multi-site policy manager, which is another application to be able to manage these. Okay. Let's start with stretched fabric. Okay. It is a single ACI fabric which is spread across multiple physical clusters. Cisco has validated up to 3 sites. You see, that's the maximum they have validated. So initially it was only 2, and then in one later release, now I keep forgetting all those release numbers, the minor update was adding a 3rd site. Okay. So how do you connect these sites? As I mentioned, you could have just dark fiber, probably an expensive option. A dark fiber, make sure you use long range QSFPs, even though they have a QSFPs which can go 40 kilometers. And I think I lately read there's something long range which is even higher. But the ACI design has only been validated for stretched fabric up to 30 kilometers. Okay. So duct fiber would be an option right there. DWDM. I would think you pretty much use it over some metro fiber typically. And Cisco has validated this up to 800 kilometers. Okay. And then the Ethernet over MPLS configuration of pseudo wire. You have to ensure that the switches in between, whatever devices in between, they are going to be transporting LLDP, because that's how they self-assemble. Remember, that's a crucial requirement for self-assembly. So initial transport has to support LLDP. So you can't have like real basic layer 2 switches which may not transport LLDP. You've got LLDP with vendor TLVs in there. So there it shows you. Sorry about that. The pseudo wire, and of course, the maximum round trip timer supported is 10 milliseconds. Well, the connections.
Hello, Elizabeth.
Yes.
Just so you know, your audio is breaking up at my end. I don't know if everyone else.
Yeah, let me check with everybody else. I might have to go ahead and switch to.
Elizabeth?
Yes. Let's see. Okay, seems like it's okay. Student who had that issue, you probably want to dial in, unless you're already dialed in. Which student was that? I couldn't see. Does anyone know who was the one who just spoke to me? Did you all catch the name of the person who just told me that there is an audio issue? I did not catch because I didn't have that interface open. Thanks, Tom. It seems it's okay for most students. Anybody who has an issue, please dial in. Now, if it affects everybody, I would try and use my phone, but it seems like it is affecting only, yeah, if it's okay for you all, some of you, that means it's not my end. It typically means it's your end. Thanks. So Ethernet over pseudo wire essentially has to have 10 milliseconds round trip time. You've got to be careful if you're using a DWDM connection.
It's hi, Elizabeth. It's Greg.
Yes, Greg. Sorry, I had to view the chat window, and of course, my thing is Greg. Can you hear me? So here we are with a discussion.
I'm good.
Okay, who's that now? Please don't type it in the chat window. I can't see the chat unless I end the whole sharing. I cannot see it. I don't have another machine up. So speak to
Elizabeth,
me.
can you hear me?
I can hear you.
Hello?
Okay, team, I'm just going to go ahead and wait for Greg to show up so I don't keep having to stop sharing and sharing each time. Okay, let's see who just joined me. Greg, if you can hear me, let me know. Greg?
Can you hear me?
Yes.
Okay, I rejoined with another phone. I think the audio issue was at my end.
Yes, I figured that because all the other students heard me loud and clear. That's why I kept saying, dial in, dial in.
Yeah, it took me a while to get situated, but I'm situated. Thanks. Sorry for the interruption.
Okay. Thank you. So pseudo wire, yeah, over, if it is Ethernet over MPLS, most likely to be done over DWDM. Just make sure that you have QoS implemented over this connection. And the reason being, you want to make sure that we give priority to the COOP traffic, the MPBGP traffic, ISIS has to form the routing table, the VXLAN, if you have any particular data application which needs low latency, you want to make sure you give priority to those devices, or mark the traffic such that the intermediate devices between the two sites would go ahead. Those which are used for your MPLS design, they should be able to prioritize your traffic. So you want to go ahead and keep that in mind. Now, the guidelines about the transit leaf and the border leaf. What is a transit leaf? A transit leaf is the yellow ones that they have highlighted. It essentially is the one which needs connectivity to every spine. You see how this is designed? There are some leaves here. They are not transit leaves. They are in each side and they only connect to local spines. But these are called the transit leaves. These have to connect to the local spines as well as the remote spines. So if I'm on data center 2, data center 1 spines would be considered remote spines. And similarly, if I'm in site 1, these would be considered the remote spines. So if you have a stretched fabric, you have to ensure that this transit leaf is essentially connected to all the spines. No special requirements here to make a device a transit leaf. They've actually been supporting this since a 1.01 probably. So no special hardware requirement there. And of course, all future releases have been, or all releases after 1.01 have been supporting, all software releases have been supporting this requirement. The question is, should you have the border leaf a dedicated entity, or can these two, like they've shown you, sorry, I drew the border leaf on the wrong switch, that's a compute. So example, this is a transit as well as a border leaf, you see? Why? Because these leaves are connecting to the other spines as well as connecting to your layer 3 out. Question is, should you have it do both? The best practice would be to have a dedicated border leaf. That means the leaves that connect to the WAN should be a separate set of switches, and the transit leaf should be a separate set of switches. That would be best practice for scalability reasons, not running out of TCAM space. So there's guidelines about, hey, stretched fabric design. These are the factors. Depending on the hardware that you have, you may run out of TCAM space if you use the same switch for border and transit leaf functionality. So the design is dependent on the hardware version as well as software version, which means capacity is dictated by both of these. So that would influence your, should I have the transit and the border leaf on the same device? Now, other design issues that you would come across, if I have multiple border leaves. Okay, so if I do have in this example, I'd like to maybe in the next one I can draw it. Maybe not here. Let's see if I have a better design here. Okay, so if I have one border leaf, see, I have a border leaf, or in this case, I have two border leaves here and two border leaves here. Okay, now, can I use these for more than two? Can I use them as border leaves for the WAN connection or to a firewall in this case, but to a WAN router, for example? Can I use more than two with the same VLAN encapsulation? It does depend on the hardware model. Also depends not so much on software, but I would say more on the hardware model. Okay, then can I use static routes instead of dynamic routes? Can I have more than two border leaves? Okay, can I use the same SVI? Now, if I typically use the same SVI on two or more border leaves, what it actually happens is it results in, suppose this was a, oops, why does it not erase my, this was not a firewall, and I had 3 devices connecting, routing, right, layer 3, so connecting to a WAN router. And I happen to use SVIs over these links, which are using the same VLAN encapsulation for the SVIs, okay? Now, what happens is this would be considered, because they're the same VLAN, from a layer 2 perspective, the external site would be a bridging domain. Now, technically, I do not want a situation where traffic may go out into this flood domain and then come back into this. So I've got to keep some factors in mind to avoid such discrepancies, especially when the border leaves are in different WAN sites. So I have those factors to be kept in mind. And of course, if I have a VPC connectivity to the border leaf, there's also some design considerations you have to factor in about the model of the hardware. You actually have to consider the model of the hardware. So if I had one, and then maybe a third data center also, and a leaf here, and they are all connecting to WAN environment, and it's part of the same layer 3 out. And each one of these use the same VLAN encapsulation for the SVI. Well, it'd be disastrous if I had traffic go out towards the WAN router, bridge itself, and get back in here. That shouldn't be happening. So that's why we have to consider the type of hardware we use. That's part of border leaf design considerations. Border leaf is any switch that you select with a layer 3 connectivity between the fabric and any peering router. You also have to consider these issues. You can see how I have firewall, and it's very likely that you may have static routes to your firewall. So if these switches are not cloud scale ASICs, kind of like cloud scale would be your generation 3 onwards. So if they are generation 1 or generation 2, you would be restricted to configuring only the 2 static configurations would be an active and a standby, like in this case, one in one data center and the other in the other data center. That's what you would be restricted to. But if you had cloud scale, you can actually go ahead and implement the static routes to the firewall, 2 points of border leaf connections with static routes in one data center, and 2 or more with static routes on the other data center. So you can see that clearly that is this is only possible with cloud scale. This is possible with any version, but more I would say this was probably not flexible in design. So I would say this is probably an older approach, the one on the left, and the newer approach would be the one on the right. Okay. So you can use static routing, you can use routing over EPCs when you have cloud scale, not a problem. And then you can, if you don't have cloud scale, you shouldn't have a problem if you're using dynamic routing protocol. Static routing has a problem, dynamic routing will not have a problem. And if you're using VLAN encapsulations over the SVI, if you use a different VLAN encapsulation over the SVI in the different data centers, you should be okay. Okay. And this is what I mentioned. If you are considering the border leaf and the transit leaf to be one and the same, you will have to consider route filtering in order to optimize the size of your TCAM. Okay, so the routes that you learn may be filtered in order to optimize the TCAM size on the border leaves. The failure scenarios. Have they shown us all? Let me see. Nope. No, they haven't shown you all, but let's look at a single link failure. Okay, this one's not showing you the, it's making it appear as if the all the links between the two sites have failed. That's what it's making it appear. This could be a well, luckily for us, ISIS is running here. That's the protocol which creates the routing table between the VTEPs, which is a very, very crucial underlay protocol. If it's a single link, as long as you have some multiple links, ISIS is going to work fine. It's going to automatically recalculate a better path or whatever available path. So that would be fine if it's a single link failure. Okay. Now, if I did have a situation where this APIC fails, you could keep continuing to make changes here. Okay, or let's say even this APIC fails because we have three, remember, three shards for each table and they're replicated 3 times. Replicas are always 3. You can have multiple shards. So I just mentioned 3 because that's what the picture had previously. Replicas are always only 3. So let's say we have the replicas over here, replicas over here, replicas over here. Should this server fail? Okay, we still have 2. 2 is like the majority. So these 2 will take over if the server number 2 was the leader for certain shards. 1 and 3 will take over a leader role for those shards, and it will continue to work. That's a single APIC failure, should be fine. Now, then we are faced with what happens if the connectivity between these sites are completely lost. Can you make changes? On this end, yes. We still have majority, so you can actually go ahead and make changes. But on this end, no changes. You cannot. It's actually in what is called minority role, because the APIC cluster, it knows internally that there were 3 in the cluster and 2 are just not there or not reachable, so it won't let you make changes. Okay. Now, if you see that the entire site is, or this is going to take some time, there is a workaround, but I'll tell you the issues with the workaround. So you may not want to make any changes. This network will continue to work fine as is. You can migrate workloads across because you still have the spines, and the APIC here can get informed about migration of workloads and so on. So it'll continue to work fine, but I wouldn't recommend trying to recover the site and make changes. And I'll tell you the reason why. I would hope that this link is restored quickly, and then they can synchronize and become a healthy cluster again. That's my best hope. If it doesn't, we'll look at what we should do. Now, what if these servers are completely lost or down and you are forced to make changes here? You cannot, as I mentioned, because there's only one. And what you can do is you can set up. When you set your initial deployment, when you do that, okay, suppose this is 1 and this is 2 and this is 3. Okay, the APIC does ask you if you'd like to set up a standby APIC. Okay, and it does ask you this question, and you'd say, yes, I'd like to do that, and you can give it the node number 2. Okay, so you can add it into this cluster, but it'll keep giving you cluster IDs and conflict, cluster ID and conflict, cluster ID and conflict. So what do? You get this one off, add this in, and then these will be in sync. So I'm actually preparing a standby APIC should I have to use it, just in case something goes wrong. Okay, so this is going to be in sync, and after it is synced up, I would power it off and configure, because this is traditionally being UCS. UCS has a SIMC chip, CIMC chipset. So you can do remote power on when needed. So you keep it cabled, but you can remotely power it on when needed. Okay, it's like the HPILO chipset. That's what a SIMC is on a UCS. So you're going to go ahead, power it off, keep it cabled to one of your leaf switches, and then go ahead and put this one back in. So essentially, when things are working, I do have a standby controller. Bear in mind, I do have these 1, 2, and 3. I also have a standby controller in place, which is powered off. Now, when I do realize that these two are completely out of the picture, something has gone wrong, it's going to take a lot of time for me to go ahead and get these back up and running or even restore them. What I could do is power the standby controller. Now, before I power it up, it will give you an error saying that the controller number 2 had a different, remember, these have their own chassis IDs because they have their own internal IDs, and it will give you an error saying this was a different switch. So you'd have to decommission this one. You'd have to decommission this particular switch out, which is the old one, and your standby controller can now go ahead and behave. So it will sync up. Now that it's synced up, you can make changes. Okay. Now, here's the other thing you would do. Whenever 1 and 2, you've had some maintenance issue, maybe some power supply failures on both those boxes or some other issue, whenever they are fixed, You turn it on. Of course, this two cannot join. Okay. What I would do is I would say, well, these two are here. They have the configuration. Let's go ahead and they have the latest update. Suppose this has been on for about 10 hours and this has not synced up. Anytime it has not synced up for 7 hours, that's the max, it will not join the cluster anymore. This will not form a healthy relationship if you power it on after 7 hours. In fact, forget 2. 2 is not going to join because this 2 is already there unless you decommission this one. So what I would do is I would clean these nodes up. You can go into the command line and you can go ahead and say ACI diag touch clean, and then ACI diag reboot. However, you can only have node number 1 join because I already have 2 and 3 in the other side. So if you really want to have the 2 join again, you would actually have to decommission the 2. There's an option to decommission the 2 at this site. This is 2 and this is 3 and this is 1. This can join happily. Clean it up, reboot it, it will sync with the existing 2 and 3 here. But this cannot join unless I decommission this. And then this one can join. Now, a good idea would also be to go ahead and clean out the switches. Okay, notice I'm putting 1, 3, 5 because typically we always design it with some form of VPC. So I'd clean out 1 and 3, clean them out. There's a command on the switch to clean the config, reload them. Once they have synced up and pull their config down again, 2 and 4, I would clean it up and have them reload again. So that's what I would do if I really, really had to go through that nightmare of, hey, my sync is gone. It's gone back home because they've not synced up for more than 7 hours. I would have to do this. Okay. That shows you prepare a standby controller, makes configuration changes in the case that the site with the 2 APICs become unavailable for a longer time. You'll just have to follow the procedures that I mentioned. Well, if you've made significant changes on that site number 2, clean it up, clean all the nodes in the first site, and have them join the cluster again. Okay. And then, of course, if I think my first site is my main site and I want 2 APICs there, I would decommission that initial standby, which has become the active one. I decommission it and get the number 2 of the first site back into the environment. Golf. Golf deployment essentially means, look at this diagram. I have WAN connections. To the spine. Versus WAN connections right there. I'm not drawing a VPC, misleading. My drawing will be misleading. That's a layer 3 connection, I'd like to say. So this is a WAN connection on Leaf, and version 2 introduced layer 3 on Spine. WSPF. Advantage, single BGP session for all tenants. In fact, that session is configured in the infrastructure tenant. And then those layer 3 out connections, the session will be called your layer 3 out node profile under layer 3 out connections, and then it's made available to other. This is ideal for a provider environment where you would have a lot of tenants. In other words, if I had 100 tenants, it means at least 100 VRFs. Had 100 tenants, each tenant with at least 2 VRFs, that would mean 200 VRFs. So I would probably go with this approach, a layer 3 configured in the infrastructure tenant and then made available to other regular tenants. Now, if you don't have a lot of tenants, you can stick with this. The second option, which is the layer 3 on the leaf. Okay. So it is OSPF protocol that we would be using here, peering with what we call the external device. It will need only one single BGP session rather than right here. Okay. You can configure these through either of these, GUI command line or the REST API. It shows you that it's supported on all the Nexus 9000 CV switches, 9500 line cards, and the Fabric modules. There shows you only a single Golf provider can be configured on the spine switches for the entire Fabric. You could configure it on multiple switches. Okay. And you can also use the same spine switch that you use for what's called multi-pod deployment. You can use the same one. That's what it's actually trying to tell you here. Golf can be deployed on all switches used in multi-pod deployments. So since 2.11, they've started supporting that same spine switch can be used for the multi-pod exchange as well as for the WAN connectivity. If you're configuring Golf on multiple spine switches, make sure you configure it on one spine, wait for the control plane to converge. What does that mean? Make sure the routing updates are showing up, and you can determine that the control plane is converged by doing a ping. After that, you configure on another spine switch. What you typically do is in the infrastructure tenant. Oops. I would need to configure the layer 3 out. Okay, that would be done in the infrastructure tenant. And this one, this configuration that I configure will be given what's called a provider label. For whatever, when I do it in the infrastructure, a layer 3 out, I would go ahead and put, there's a field on the layer 3 out where you would provide a label saying it's the provider for your routing updates. That's what you're trying to say. You put a label on it. Okay. And then in the regular tenant, you're going to define layer 3 external EPGs, okay, with the subnets in the regular tenant on the bridge domain subnets, you'd have to check the box saying advertise externally. Okay. And what do I need other than that? And then, so I have a layer 3 external BGP. Of course, that means I would need to set up contracts between this EPG and my applications EPG. So every tenant, tenant A, for example, would have a layer 3 external EPG, let's call it A, which identifies the external routes. Or it could be quad zeros if you want it to behave like your default route. And then you have within the application, an application EPG. So these two would need a contract. Okay, so communication between the application EPG and the one that you define. This is actually for the golf purposes. Now in this one, I would use a consumer. On the consumer tab, I'd have a label. The label should match the label we've configured on the layer 3 out of the infrastructure. It should match. Okay. Now, the BGP session. Is going to actually go ahead and advertise. So this provider, this is going to advertise the routes that you have marked in the regular tenant as advertised externally. So they just have some configuration requirements. It shows you the spine switch. Your layer 3 out is provider label. Okay. The EVPN session in the provider advertises the tenant routes that are defined. Okay. So there it shows you if you're configuring 3 golf connections, 1 provider and consumer label for golf, and you actually use the quad 0 aggregation, that's for export, your APIC will export all routes through all golf connections. That's going to be the case. Even if you do it only on 1 golf, this is going to be exporting all routes through all the golf configurations. Well, if there's direct peering between the spine switch and your data center interconnect router, that means if you're going to be using that same router for inter-pod network, you're going to be configuring static routes. That's what it's showing you there. That's actually telling you that the default policy restricts the routes to 20,000 in the longest prefix match table. Where there are 2 layer 3 outs on 1 spine switch and they pair with 2 data center interconnects. Remember, layer 3 outs typically mean 4 WAN connection, but suppose you use that same for your data center interconnect. It says your tenant routes will be sent out both, even if you do it on one of them. Route leaking cannot occur if you aggregate. Aggregate is sending your default route. Okay. So these are some limitations when you implement golf. Right there it shows you this is where we are using the same routers for both inter-site as well as WAN. Same router, and that means same spine switches. It's for inter-site as well as your WAN connectivity. This is easier to troubleshoot. But this would be reduced cost. Sorry. Yes, reduced cost when you have the WAN being used for both inter-site as well as for WAN connectivity. You got reduced cost here. A little complex to troubleshoot in this situation. Little, not too difficult though. That's your golf deployment. That's some providers tend to use golf over connecting your layer 3 to the leaf switches. Multi-port is probably many of you may have or will be deploying. Okay, it's one cluster which is broken up into what is called PODs, pods. You can use it within the data center. Reasons could be, I want separate fabric, separate administrative, not separate fabric, sorry, separate fault tolerant domains. Not administrative, it's one administrative domain, it's the same cluster, but separate fault tolerant because this has its own ISIS, its own MPBGP, its own COAP instance. Okay, so the reasons could be the way your physical data center, within the data center, it's usually dictated by size. Okay, size could influence pods. It could be dictated by physical cabling. What if your data center is in different buildings? So you may have limitations of being able to connect the leaf to every spine, because if you think about it, within a pod, you need the leaves to connect to every spine. What if your leaves are in a different building and you cannot accommodate that physical connectivity? Don't want to spend so much, you can have them in different buildings, could be different pods. Okay, that would be different physical locations. Okay, supported designs, of course, within the data center. Okay, 2 different data centers, 3 data centers, and just a generic inter-pod network with some requirements. Okay, so this layer 3 network does have some requirements, and we're going to see what those requirements are. Multicast support. So why do we need multicast support? I have a bridge domain in one of these data centers, which is spanning multiple devices. Let's say I have a bridge domain 1, and I do span bridge domain 1 here, bridge domain 1 here, bridge domain 1 here. Some of the leaf switches have devices or endpoints which belong to bridge domain 1. Now, every bridge domain has its own dedicated multicast address assigned. That's called the multicast group IP outer. It's called GIPO. Whenever it's handling the broadcast and multicast data plane traffic, I'm not putting you, unknown Unicast is handled differently by default unless you turn it off. So broadcast and multicast data plane traffic, the VXLAN destination IP is the bridge domain's group IP outer address, which is actually a multicast address if you think about it. Now, in multicast networks, this is a generic question. In multicast networks, how do routers make the decision? What protocol is involved for a router to decide, hey, I need to send a copy of this frame to router 1, router 3, and router 4? What protocol is involved there? Anyone? Multicast technology. Sorry, I am going to have to stop my chat or stop my share in order to examine what the student responded. No, Anycast is not a multicast IP. So, sorry, Ginger. Anycast is always a unicast IP address. In a multicast network, how does a router decide on which ports it should replicate traffic? Anyone know what is IGMP used for? What is the purpose of IGMP in a multicast environment? What is IGMP used for in any multicast network? Anyone familiar with that? What does IGMP do? Let's see. Who? Layer 2 table with the group address. Yes, that is kind of correct, but actually IGMP queries are initiated only by layer 3 devices. Okay, IGMP queries are actually layer 3 devices initiating them. In other words, IGMP joins are sent by your end clients saying, hey, we want to join this multicast group. That's the purpose. It is actually meant for layer 3. Joins and queries are actually, so join is meant targeted for a layer 3. Query is initiated by a layer 3 device, never by a layer 2 entity. It's a different story. The switch listens to these. Okay, the switch actually knows, okay, I saw this join coming in on port 1/5. I saw the join coming in on port 1/8. But the join message is intended for a layer 3 entity, because only layer 3 entities send out IGMP query saying, hey, anybody out there who needs to join the multicast groups, let me know. Okay, so in this particular scenario, every bridge domain actually has a multicast address. So the only way the fabric knows which physical leaf switches are members of the bridge domain is using what's called IGMP. Okay, which physical leaf switches are members of the bridge domain. It knows it because of IGMP. So we have to make sure that these IGMP messages are transported. What happened to they're transported across this inter-pod network. We have to make sure when a bridge domain is stretched. So that's why it says you would have to ensure the devices in the inter-pod network support multicast, and the method of multicast used, multicast routing, which helps these switches, helps the routers in the cloud maintain the state. And it's both, they have to support by their PIM. I'm talking about these devices. Now, another thing they are saying is DHCP relay support. So why do I need relay support? Let's look at this diagram. Let's pretend as if this pod, this is the first pod, it discovers, goes through discovery, you register the devices. Question, where do the switches get their VTEP IP addresses from? Where do the spine and leaf switches get the VTEP IP address from? Every spine and leaf needs a VTEP IP, so where do they get that from? Okay, let me go ahead and stop my sharing so I can see who has responded. And where is the DHCP server? Set up during the APIC config, that's correct. Okay, so if I were to look at this particular diagram, we are going to be presuming that the left-hand side APIC is set up and the APIC has its DHCP range configured. So now when I need to initialize this side of it, these spines turn on and they need an address. So who are they going to send it to? The first connecting device right here, your router in the inter-pod network. Well, this should be configured with DHCP relay. So it can relay that request. Remember, DHCP requests are always broadcast. They do not pass through, so we need DHCP relay. They should be able to relay that request through. And that's the reason why they've said you need DHCP relay support for interpod. Well, the only routing protocol, you can use static, but the only routing protocol that is supported for the MPBGP is dynamic routing over the IPN is OSPF. So your IPN routers should support OSPF. Okay, then did I ever mention the default MTU in the ACI Fabric? Probably didn't. So the leaf switches, they are set to 9,000 bytes by default. So do your VMs or bare metal servers send 9,000 bytes? Do they? What if they don't and they're only sending 1,500 bytes? They don't send any jumbo frames. Well, think about it. When it goes into the fabric, it gets encapsulated with VXLAN header. Okay, so there we actually have additional header added. So if all my endpoints are 1,500 and lesser, just add another 100 bytes to it. So make sure the MTU in the IPN is set to at least 1,600. Okay. If your endpoints are likely to send 9,000, make sure your IPN, which is your spine connecting to the generic IP network, these switches should support 9,100 bytes. Okay. Then there is exchange of control plane information going on between these switches. Clusters replicating. That means we have APIC clusters replication traffic, MP, BGP, EVPN. By the way, this is multi-pod. What it does is it takes your control plane traffic like your COOP database information and sends it that's control plane traffic. I've got to make sure that it is actually sent across correctly. So I have to configure for QoS. Now keep in mind at the final outcome, these are Ethernet frames being sent. Now, my EVPN traffic, my actual data traffic, they all have an Ethernet header. But they also do have an IP header. IP carries the priority diffserv code point. On the IPN switches, on the IPN devices, ensure that the cost to diffserv code point mapping is correct on the ingress side, and then on the egress, diffserv code point mapping to cost is also consistent. What am I trying to say? Let me see the diagram if we have one. Better diagram would be, okay, so my EVPN has a certain diffserv code point, but this IPN device is not in the management, it's a external IP network, so it's probably not under your control. So IP is always encapsulated with Ethernet, and Ethernet has its own, so IP has its own diffserv code point header, and Ethernet has 802.1p, which is cost value. Now on ingress, if it reads this value, they have a table called cost to diffserv code point mapping table. Now suppose the diffserv code point was 46. That's like expedited forwarding, but the cost header was 4. Typically, cost header would be 5 when it's exiting from the spine. But suppose in this table on the IPN, it basically says cost header of 5 becomes a diffserv code point of 40. Now inside here, it travels with a 40. Now when it egresses out, probably uses a reverse table. And 40 might be mapping to 4. So even though this was sent out with a 5, because of the table in the IPN, it became 40. And then on the egress side, that became a 4. And here, a 4 is probably only 36 maybe. So it really lost what it should have been, 46. And by the time this spine receives it, it's become 36. Not ideal. So you've got to make sure the mapping tables here are consistent with, it should say, if it is 46, should be 5. So 5 should be 46, not 40. And then here, hopefully 46 also becomes 5. Sending it out. Very important from a QoS perspective to make sure our traffic does not slow down. That's what it tells you. Okay. So the IPN is simply an extension of your ACI network, and you need to make sure that the VXLAN tunnels can be established. It does that by default as long as you take care of these requirements. From a design perspective, okay, you don't have to have every spine in the pod connect to the IPN. You may actually see that in this. Nope, they don't reflect it in any of these. None of these are good diagrams. But I could just scribble over it and say, well, here's what they mean by that. Suppose I have 4 spines. I don't need all 4 spines to connect to this IPN. I can just use 2. Okay, maybe there are 6 spines here. I can use just 2. So there's no need from a design perspective. Okay. It will not allow you, you cannot do interpod by directly connecting spines. You cannot do this. So what do I mean by that? You cannot have spines directly connect to spines. Not possible, not supported. Maybe in the future they will do that, but not at this time. Okay. You also need to remember a requirement. The spine line cards are a minimum of 40 gig or 100 gig. Those are the only types of line cards on spine switches. Remember, this one, this fabric link has to be 40 or 100. So the only line cards for spine. So that means this device whatever device you connect to for inter-pod network has to be at least 40 gig or 100 gig. Okay. Then all the IPN devices should have physical interconnecting path. What do I mean by that? Between, say, this is an IPN. It should have path here, path here, path here, path here, path here, path here. If you don't have this, you may have issues with your broadcast and multicast traffic, which is essentially being enveloped with a VXLAN header, which has a multicast address. We may have IGMP join messages going across. If they don't have physical connectivity, those join messages might go across some routers which do not maintain state. So you've got to be careful. They don't maintain the multicast. For those groups, for those multicast groups of the bridge domain address. So I have to ensure whichever IPN devices direct. So I don't have any device in between which doesn't maintain the state for the purposes of the multicast groups, group addresses which are assigned to the bridge domain. Okay. Well, Spine only supports these line cards, so of course your IPN devices must support the same speed. Okay, you can look at the sequence of events in multi-pod provisioning. It's actually shown you here. The first pod is set up like a normal single fabric environment. They discover themselves and the APIC assigns all this. So the first pod is going through, you have this discovered, all the leaves and the spines. This is good. Okay. We are going to configure layer 3 out. Okay. So okay. That would be OSPF, all you know. That's why it says provision the interfaces on the spine facing the IPN. So that's what the option number 3 is. So basically, this part of it is taken care of, at least this part. Okay. Now we are going to pretend that we power these on, or at least one of the spines on. Okay, turn this on, connect it to the IPN. As soon as the spine turns on, remember, it sends a DHCP request. So what should I have done? This IPN device should have DHCP relay. So I would say not to the spines. Where do they need to relay to? APICs. So the spine turns on, sends a DHCP request. Okay, so that's what the step number 4 is showing you, sends a DHCP request. Okay, that request is being relayed back to my APIC right there. Okay, where is my response? You see how the APIC is sending the response? Hey, here's your IP. That's basically saying, response, here's your IP. What does this APIC do? It assigns that IP to its interface. It installs a static route to the APICs in pod 1. Notice what I said, static route to the APICs in pod 1 with the IPN as the default gateway. Because who was the IPN? The IPN was the relaying device. That's how it knows, right? Because the DHCP response always carries the relay address. You should always remember DHCP always carries that as part of its response. So it conveys the relaying device IP. So my spine is going to go ahead and add a static route to the APICs. Why does it want a static route? Okay. After it knows, it's going to go ahead and talk to the APIC and download its configuration. That's why. Right there. So once it gets the response, it is actually going to talk to the APIC, get its layer 3 out config. Well, that probably configures OSPF here. So it has connectivity. Remember, this is a layer 3 out. So it establishes connectivity. No need to have the static route anymore. So what does it do next? It says, hey, guys, you can all now become DHCP clients. It's basically saying, I'll relay your request to all the other devices as they turn on. They are all going to go ahead and relay their request. So they are discovered, assembled, and now you can turn this one on. It'll form its cluster. Okay. That's kind of what happens, and you've got to take care of some of these requirements. That just shows you that you need to provision for the QoS. As far as the design for multi-pod fabric, it's kind of like the same as what we saw in a stretched environment. You would have single site laws. Remember, these can function that if it's only one APIC, you can't make any changes. Okay, you can make changes here. One, you cannot make. Entire pod fails here. Both the APICs are gone. Introduce the standby controller as we saw earlier. This is the design guideline for your 5-node cluster. They've only shown you 5-node in this particular example. Cisco has published a 7-node APIC cluster, 9-node APIC cluster, 11-node APIC cluster. This is just showing you it's possible to even have multiple pod environments without APICs. Notice? It is possible. The last deployment is, of course, about the team have a question. Would you, it is about 12:09. Would you rather I just finish the chapter, which would take probably another 20 or 25 minutes, and then call it a lunch break? That way, those who are done with the lab can kind of wrap up. Or should I go ahead and give you lunch break and then continue with the chapter? So we have about 20 minutes, 20 to 25 to finish this chapter. So give me a yes or no, depending on how you'd like to go about it. If you don't say anything, I'm going to assume that you're fine with me extending it by another 20, 25 minutes. Tom, you're okay. Wide, okay. I don't know, don't see responses from the others. I'm going to assume that you'll are fine, because I did say if I don't see a response, I'll assume you'll are fine. So this is a more costly deployment, multi-site. Multi-site is independent clusters. Now, this cluster itself could be multi-pod if you want it to be. Okay, there's no mandate that it cannot be multi-pod. The cluster itself could be multi-pod, but they haven't shown that to you. It's essentially what we call an independent cluster, an independent cluster. In the past, you would be managing them as two separate entities. That would be multi-site. Okay, in the past, you would be managing them. So 3.2 is when they introduced multi-site with a multi-site policy manager. But prior to that, it used to be just two separate independent clusters, and you would have some form of layer 2 connectivity between them, and you go with that. That's what we had. That's the dual fabric design that we saw in the first slide. Multi-site is saying, well, you would introduce a product, install a product in either one of these sites, or maybe you can spread that product. It's also VM cluster, so you can have it in different sites if you need. But it's a product, which is a cluster of 3 VMs. This ensures more like a single pane of glass for managing stretched applications. Okay, that's the purpose. Okay, so each of these are separate administrative zones. Keep that in mind. They are completely independent administrative zones because they are two separate clusters. But you can go ahead and have them become one cluster. Sorry, not one cluster, but pretend as if they are. Now, there are some hardware requirements for multi-site. Your leaf switches can be any, I don't care. But spine switches, they have specific hardware requirement. They should, if they're 9300s, at least a minimum of 9364C, that's the minimum. Or if they're 9500s, you need line cards which have EX or FX in their part number. This is for line cards. And then you need fabric modules. Fabric modules should either be E or E2 fabric modules. I hope everybody remembers the fabric module is the module that connects the different line cards in a modular chassis. So you need a minimum of these for spine functionality. Only then you can use it for the multi-site. As for leaf switches, we don't really care about it. So if you think about it, the VXLAN header, remember, VNet value would be a VRF for routed packets, a bridge domain ID for bridged or switched packets, and VNet value could be EPG ID sometimes. I'll talk about that. But EPG ID is also used whenever it's a BPDU frame. So the VRF here or the bridge domain here would be included in the VXLAN header. And something else that it carries, it used to be a reserved field in normal VXLAN, but currently in eVXLAN, that is equal to the source EPG. So if you're sending VXLAN traffic over across, and this is a separate EPG, separate fabric, a separate cluster, how does it translate into an EPG here? How does it translate the VNet values into values at the destination fabric or the destination cluster? That has to be done by these spine switches at line rate. That means it shouldn't introduce any latency. That's the reason why these are expected to be one of those switches that I mentioned. So you can't use any regular spine. It has to be the ones that I just mentioned. Okay. So there shows you that multi-site requires ACI mode leaf and spine switches. The spine switches, which are connecting this IP network, is a generic IP network, but it is also known as the inter-site network, just like the generic IP network between the pods is known as the IPN, inter-pod network. These spine switches which connect to the ISN should have met those requirements. You can have a combination. You notice these are older spines. They can coexist with the newer hardware in an inter-site topology. You're fine with it. As long as we have these newer hardware for inter-site, we are good. This is the application. It's a cluster of 3 VMs. Ideally, that should be physically in the same location. That's ideal. Okay, that's the greatest part of this. You don't have to have these VMs in every site. Can you have it? Yes, but then you would need to ensure low round trip timer. Okay, the round trip timer for this, I think it was 150 milliseconds. These VMs actually have containers. Docker is the container they use for running the multi-site application. Okay, so this application has these organized in a dashboard where you see the different sites, the health of the sites, and you have the option to import from different fabrics, certain VRFs or bridge domain information. You can see the tenants across each of these fabrics. You can go ahead and add users, AAA authentication, LDAP radius, all of that for logging into multi-site manager. Okay, and you can create a policy as a template and then apply it. Template makes your life easier. Baseline values are in there. And you can say, I want to send it to or apply it to APIC cluster 1 and thus its fabric, APIC cluster 2 and its fabric. You can go ahead and create policies centrally and make them available for the different fabrics to use. So this is what the multi-site policy manager looks like. Okay, that's where you configure the administrative. That's where you see your users, tenants, import from other sites, add a site. Okay, and this gives you the health. You can see how you can see the controllers, how many are there, what's their state, any critical errors, major errors, minor errors in each of these fabrics. So a policy template, notice we define it in the multi-site policy manager, and then you can make it available to each of these. Okay, you're still going to see and configure the APIC GUI for site local. Each APIC is a cluster. Each of them, you're going to log in for any site local policies, but anything which needs to have an application spread across these multiple sites, you would do it in the multi-site policy manager and then have it pushed to your individual fabrics. Use case, local data center, if you want to, you're good. Okay. Remember, it could be a really, really large campus, like the campus of a Walmart or a larger Wells Fargo or something, very large campus. And then you could have different APIC deployments in there, each of them their own independent administrative domain, but you can centrally configure policies and have applications stretched across. So that could be local data center. You could also definitely use it for geographically distributed. I may have APIC in the East Coast and APIC and the West Coast and APIC in the central mountain areas. So you can have 4 different APICs and then they could still be managed centrally to a lot of extent. And you can even do VM migration across these. Okay, so that's the beauty of multi-site. Though more expensive, that's the beauty of multi-site. Okay. Not only is it control plane fault isolation, but also from an administrative domain, they are completely independent. So you can see that they have used some terms here. The CP ETAP, DP ETAP, and DP head-end replication. Okay, so what is CP ETAP? Every spine that connects to your IPN or ISN. Okay, they're going to be assigned a unique IP address in the fabric to establish. They actually need to establish MP, BGP, EVPN, Ethernet VPN adjacencies with the spines in the remote sites. That's a unique IP assigned to every spine. Oops, not this one, not this one. I have the arrow already. So I'm going to say that's a unique IP. Okay, so let's just change that. Now, MPBGP adjacency is for, remember, any conversation that happens between these two, if they should happen, endpoint information. Endpoint information in here is achieved by COOP. In here is achieved by COOP. But then we need to send only for any conversations that happens, not all endpoint, only for any communication that we design for. That means we have a contract between applications across these two sites. That's when the conversations need to happen. So that's when this protocol distributes the endpoint information. MPBGP EVPN is transporting the control plane information. So in order to establish those adjacencies, every spine that is part of your ICN is actually given a unique IP here when they are configured to join the ICN. Sorry, ISN. Okay, that's unique IP. That's for control plane adjacency. That's why the term CP, that's for multi-protocol BGP EVPN to distribute the endpoint information. Okay. Any cast address for all the spines in a site. Okay. Now I'm using about all the spines, but I should particularly mention the spines which are connected to the ISN. So I don't have space to write that, but the spines that are connected to the ISN. A common anycast address for all the spines in a site, so they can send unicast data traffic. And if I say unicast, remember, data is always encapsulated in VXLAN. All the data going through is actually in VXLAN. VXLAN, if it has a unicast header or it's encapsulating unicast packet, it's got a unicast header, and that's the source IP used when it is sending it from here, and we'll use the destination IP of this spine. Okay. Now, the other value we see is for data plane. DP means data plane. Head-end replication. That's also a common Anycast address for all spines of the ISN. Connecting to the ISN in a site to transport and perform replication for broadcast and multicast traffic across the fabrics. Okay, the data plane one, it's using Anycast addresses, whether it's for unicast traffic or for broadcast and multicast traffic. These spines are given unicast addresses. For control plane transport, the spines are given unique individual IP addresses so they can form an adjacency with their BGP peer in order to send out those EVPN frames. Again, make sure your ISN supports a larger MTU. These might be sending 9,000 bytes. Adds VXLAN header, it's going to become 9,100 bytes. And OSPF is the protocol that they support for communication to the ISN and building routing table. So you can kind of see how they have this information in the table populated. You actually see that you have an endpoint, it's learned in the COOP database, right? Endpoint sends traffic, local station table, then it sends it to the spine, COOP database, and then it exchanges. You see that? These two are then going to send that update through EVPN to here. So you can see how it's also learning the updates sent from here. So according to these two spines, if they have to get to this endpoint number 2, which is a unicast destination, the traffic should be encapsulated and VXLAN header should be the data plane. That's, remember, an Anycast address. This is an Anycast address used by both of these. Okay. Now, similarly, if you look at the other table, it shows the other way around. It says, oh, my local Yep, they should have said EP1 and point 1, and then point 2 is only 4. So that's what the COOP database here would be. Okay, they actually have it incorrect there. That'll take care of your BUM traffic between the sites. It'll take care of this by itself, takes care of your unicast traffic within the site. And then this exchange takes care of your between sites. So what are my use cases? It could be a stretched bridge domain with a broadcast extension. That means I enable flooding across that bridge domain, a layer 2 flooding. Okay. The second one is I have a stretched bridge domain with I don't enable a flooding option. We'll see the use case there. I have a stretched EPG across sites. It will not have the common bridge domain, so it'll basically be sending the packets as a routed packets, not bridged. We have a stretched VRF with inter-site contracts where it becomes granular. And then we have a use case of shared services. So here's the one with a bridge domain. And I have enabled in the multi-site manager. This bridge domain is extended. The same subnet. Okay. The web EPG is extended across. And you have enabled broadcast flooding for that bridge domain, which is extended, something that you would do in your multi-site policy manager. This would be ideal for, if you have an app here, which is clustered. It will let you do live VM migration, or as we call it, hot VM migration. And of course, it also means you can have apps which are active-active. Okay, that's one use case. The second use case is, of course, I do not enable flooding, even though it's identically looks the same. It's the same tenant, the same VRF, the same bridge domain, the same subnet, and the same EPG. Identical as the last one, but you can, yes, move a VM. But that would mean for DR, it would be more cold migration, not while the VM is on, not a live migration, cold migration. That's the only thing possible in this scenario. It's ideal where you need just inter-site mobility for DR purposes. You could have a stretched EPG across sites. This is going to do, if I need a stretched EPG across sites, this is going to be between the sites. It's not doing layer 2, it's layer 3 forwarding. But for this design, I have to have 2 independent physical domains and a VMM domain. That essentially means I have to have virtualization to benefit with this feature. The EPG is stretched across the 2 sites, but they are using different subnets. I could use this design. Different EPG, different bridge domains, different subnets. The contracts are going to govern how they communicate, gives me more granular control. Again, the traffic across this is only layer 3 routed traffic, only cold migration possible. Here's the other issue. Cold migration is possible, but it is not going to be able to migrate with the same IP, because if you notice, it's a different subnet. So we're not preserving the IP. You cannot have it preserve the IP. A fifth design, I want different multiple sites. You see how they are? They are grouped as one. And then I have another group of sites grouped as two. I have to do route leaking between these VRFs. I have to do global contracts so they can be imported, exported, and imported. Okay, that means definitely the contracts have to be global. And something that is a prerequisite in this particular design would be, they say shared because it's shared across, the providers are shared across, or the consumers are shared across multiple APIC fabrics or APIC clusters. That's why the term shared services. Okay. I would have to make sure that I configure the subnet under each EPG and advertise it or share it between VRFs under each EPG configuration, not on each bridge domain. So how do you migrate your existing networks to Cisco ACI? Could be for any of these reasons. Maybe your company's operation is going through some evolution, moving away from command line to some kind of orchestration. Okay. It could be because we want more stricter policies who can communicate. It could be because we are moving towards container-based application environments. Any of these reasons, you might have to migrate to Cisco ACI. So one of the design recommendations, I do have 2 clients which took this approach. Existing apps are here. They did not move them, and only new apps in the ACI. Okay, that would be one approach. Or if you look at the second approach, it's kind of similar, but what they did do, so essentially if you look at this approach, the approach that we have, these servers not at all governed by the APIC policies. Any communication in that pod in the existing data center is solely governed by the existing data center rules. Only new apps are actually subject to the policy rules of the ACI environment. The second bullet there shows you they physically moved. This is also a layer 3. They physically moved your 7K layer 3 out. So this is a layer 3 out from the fabric. That's the second design. It's pretty much the same. You have a layer 3 out here connecting to this campus router or something. And in this case, this is a layer 3 out connecting to. So ACI does not govern any of these, except you can, that's AVS or AVE. That's a virtual host. You could, because they support OpFlex. And then you can do VXLAN as the encapsulation for the switch, so it can transmit through layer 3 connections. You can do controlling the AVE configuration of the virtualization environment through the APIC. Subject them through policies. Okay, that's the second approach shown there. Third approach, they've physically moved your 5Ks. That's a layer 2. That's a VPC, if you notice. Okay. Any communication between hosts here, not subject to ACI, but if they had to communicate with any host hanging here, subject to the ACI policy. Again, you could decide to have the AVS or AVE controlled by the APIC environment. Physically move your FEXs. The only thing you want to remember is FEXs will be single homed. You can't have FEXs dual homed. So if you're going to have the applications migrate, some components of the application migrate, establish a layer 2, probably a VPC, and then a layer 3 to connect to other networks. Okay, so you're going to configure the ACI for the layer 2 extension and also have a layer 3 out for configuring or supporting other networks. You're going to create your bridge domain, your tenant, your VRF, your bridge domain, and your EPGs. But here's what we have. I may have some servers of the application here and some servers here. And that could mean VLAN 10, there might be some servers here and some servers here. So where should my default gateway be? Most likely the default gateway might be here. When bulk of your traffic is on the, this is your traditional network, by the way. This particular one is your existing data center. So bulk of traffic is in the existing data center. Retain your HSRP here. Even this will have to bridge through, get routed by the default gateway here. But then once you migrate most of them to ACI, then you turn off the HSRP, you turn that off here, and then you enable your default gateway, which is your pervasive SVIs gets created onto the leaf. Okay, so, and hopefully you move everything, all the servers connected here, you migrate them off. Once you move everything, of course, you can turn off your existing network. An example shown here, 2 existing VLANs. So this is your traditional side, VLAN 10, VLAN 20. It also appears they're using Fabric path here. They have a layer 2 VPC shown here. They have basically, in order to do migration, Cisco recommended what is called a network-centric migration. So to make it easier, every VLAN on the traditional side becomes an EPG, which is in its own bridge domain. So it's kind of like each bridge domain and EPG together is equivalent to the VLAN on your traditional network. Okay, so there it says. That's on your layer 2. And of course, they've also done that right there. So they can communicate over that VPC. Okay. What is this one? They have only one VLAN, but they are actually two different applications, or at least okay. Now, when you move it over to ACI, that's not recommended. You don't want two different applications in the same EPG. That's really not what Cisco intended for. So you see what they've done? They've actually gone ahead and said, we're going to map it such that we're going to have right here, any other servers which move here, these are being mapped to VLAN 30, the application servers of app 1, and the servers of app 2 are being mapped to VLAN 20. And now we just basically use contracts to communicate. If there are existing servers in the data center, it will communicate to them using the contracts. So eventually, when you migrate all of these, app 1 would have its own EPG for web, and app 2 would have its own separate EPG for web. Virtual workload migrations. So existing VMware DVS. Add your new hosts. Remember, that means we're going with managed mode. Two options, VMware or AVE. This green one is an existing DVS, already in vCenter. So initially, what we would do is we would say, okay, let's not create a new, when you go with managed mode, it's always going to create a new DVS. Okay, this is actually a result of ACI creating a new one. In other words, I would essentially have to have a physical host with at least 2 adapters. Okay. On one of the physical ports, they've not actually shown you, I would go ahead and, like in this case, it's connecting to another switch, and the switch does the VPC. So one of the configurations in the APIC would be non-managed. One of the configurations. So I can actually extend the DVS, the existing one, towards and use the physical adapter, which is actually shown here, one of the physical adapters, to the existing DVS. And then I move some virtual machines over. Once I've moved some virtual machines over to the host, and then go ahead and do the managed approach, which just creates a new DVS. So I have a second physical adapter, which serves as the uplink for the new DVS. That's actually a second physical adapter. makes it easier for me to move my virtual machine, which was on the green one, to the red one. A lot easier to accomplish this as far as migration. Now, my default gateway initially was on the traditional network. Probably HSRP on my existing network. So all of these would have to send their traffic over the layer 2 to be routed over the default gateway. But once I go ahead and I move bulk of my traffic into ACI, I would turn off the HSRP here and then enable the default gateway as SVIs on the leaf switches. Okay. Well, if I'm not really going to migrate any component of the application, or if the application still needs to stay in the existing network, all you need to do is a layer 3 peering, which could be any of these protocols that we saw for layer 3 out. Okay. Finally, you can take advantage of managing layer 4 to layer 7 services via the APIC. This would be taking advantage. If you didn't want to, you could do unmanage. Okay. You can just make sure you got your ports into the right VRF, the right bridge domain. So you can do that. But when they say migration, they're actually implying would be nice to do this. So you can manage or configure your layer 4 to layer 7 devices through the APIC. You can also do this policy-based redirection. Notice what they're saying. Some traffic goes directly, the blue goes directly between the EPGs, because that's how the contract is configured. This particular subject does not have no layer 4 to layer 7 service graph. And the red one, that subject has layer 4 to layer 7 service graph applied in that contract.